This presentation is for the 11th International Conference for Internet Technology and Security Transactions. The title of this presentation is Security Analysis of Forwarding Strategies in Network Time Measurements using Openflow. My name is Alex Orozco. I am Assistant Professor at Sul-Rio Grandense Federal Institute and doctoral student at Pontifical Catholic University of Rio Grande do Sul. The authors of this work are composed by me, Charles Neu, Régio Michelin, and Avelino Zorzo. Nowadays, the complexity imposed by the wide options of network topologies implies on several strategies to increase network security. For instance, time is one of the aspects that could be used to improve network security. Furthermore, usually time may be used to detect network problems, for example, bottlenecks caused by high traffic or attacks. Therefore, due to the importance of the network time measurement, several tools were developed in the past, for example, ping, traceroute, pathchart, and iperf. But the development of those tools focus on functional requirements, and security requirements usually are not considered. One of the ways to solve the mentioned problem could be to use software-defined networks, or SDN. The main functional protocol for SDN is the Openflow. This protocol separates the control plane from the data plane. The control plane is located and managed by the controller. The controller can communicate with many switches and manage the traffic according to policies and rules. The controller uses packet forwarding algorithms for choosing a route for any packet. And in some network controllers, such as POCs, for example, it's possible to choose this forwarding algorithm. Some researchers propose to increase network time measurement reliability using Openflow, or how network time measurement could be used as a way to facilitate attacks on Openflow, but those researchers did not consider the impact of altering the algorithm in his analysis. Our work investigates how to provide POC's Openflow controller packet forwarding strategies could be applied to compromise the network time measurement reliability. Our work also shows that the way those strategies are applied could prevent against new attacks that need to trust on network time measurement. Hence, some experiments were performed to show the impact of the packet forwarding algorithm on network time measurement, either to compromise or to help in protecting the network. Some attacks, such as delay attacks, exploit the end-host bandwidth bottleneck measurement mechanism. In order to solve this vulnerability, Karam et al. Discussed the Openflow contribution based on bottleneck bandwidth estimation and network coordinate measurement. To achieve that in their work, they take into consideration two entities, the prover and the verifier. The path between those entities traverses a network domain managed by a network controller. The bottleneck bandwidth estimation is obtained using a packet pair technique, and after that it's possible to measure time in a more accurate way, based on the mean of round-trip time or RTT latencies. This may be used by the hosts to discover the network coordinates relative to the other hosts, for example, to establish the network topology. Although the Openflow protocol could be useful to offer a more reliable network measurement, an attack exploring that combination was proposed by Tsonchek et al. This attack is a sophisticated inference attack that an adversary can use to learn more about the network. In this attack, a stream of time probes and a stream of testing packets are sent simultaneously to the target network. Time probes are ping packets and RTT depends on the controller load, and test packets are spoofed packets. The action of sending different test packet streams can offer enough information about a network behavior. For example, considering the scenario in which an attacker sends packets to a target destination host from different source hosts. If the RTT for all packets are similar, then it's very likely that the target destination is a server, or an important host in the network, since all source hosts know the route to the target host. However, if the RTT is different, it might mean that the controller is processing the packets to discover new rules. Then the attacker can build a graph that represents the network topology. Hosts that have several edges in the graph may be critical to the network and ideal target for DOS attack, while hosts with few edges may be less frequently used and an ideal target for the adversary to infect. The controller performance depends of the packet forwarding algorithms used. Indeed, Vageni analyzed the main forwarding algorithms offered by the POX controller. These algorithms are L2 learning, L3 learning, L2 pairs, L2 flow visor, and L2 multi. This set of package forwarding algorithms was applied to our experiments in order to evaluate the impact of Openflow configuration on the reliability of network time measurement and also to reduce possible security attacks. The experiment was simulated on Mininet 2.2.1 using an Intel Core 2 Duo P8700 with 4 GB of RAM. We used Ubuntu 15.04, a Linux kernel 3.19, and a POX controller version 0.2.0. We developed a set of experiments to show that different algorithms can affect the measurement. This attack masks some types of attacks, but this can be used to avoid some types of attacks. Our simulation is based on a mesh network composed by 12 switches. Each switch was linked to the controller and the host. They were configured to operate on Openflow version 1.0. To evaluate the communication, we used RTT. The links were configured with a bandwidth of 10 megabits per second and 5 milliseconds of propagation delay. On the simulation, a host connected to switch S1 will communicate with the host connected to switch S11. For each experiment, the POX controller was configured to forward packets based on each forwarding algorithm. Each experiment was performed during 370 seconds to allow idle timeout and hard timeout events of flow removal. On each round, the payload was increased from 56 bytes, 4, 8, 16, 32, and 65 kilobytes. We collected the RTT average and standard deviation from each payload, and the experiment was repeated 6 times. The second experiment measured the impact of each algorithm of each forwarding algorithm on the inference attack. The experiment was replicated 10 times for each algorithm, and also for the different size of payload. We reset the environment for each packet that was sent. The main objective of this resetting was to analyze the worst case of each packet, that is, the creation of new rules and roads. As can be seen in the graph, when the packet size is small, the RTT are similar for all algorithms. When the packet size increases, the RTT value from L2 learning and L3 learning algorithms are equivalent, but the L2 pairs, L2 flow visor, and L2 multi RTT values are more than twice smaller. This clearly shows that for big packets, the influence of the algorithms are significant. Based on those results, supposing that an Openflow network was used to prevent delay attacks, and the controller was configured with L2 learning or L3 learning, the change on the algorithm to L2 pairs, L2 flow visor, or L2 multi could mask a delay attack. Hence, it's possible to perform the attack if the configuration of the controller is not performed carefully. The results from the second part of the experiments are related to discover the RTT for a packet that has an unknown rule to the switch. We called that as peak time. As can be seen, when the packet size is small, all algorithms except L2 multi produce an equivalent time. However, bigger packets impact directly on L2 learning and L3 learning performance. This graph shows the comparison between the previous graph. It's possible to realize that for big packet size, peak time and RTT are similar when using L2 multi, L2 flow visor, and L2 pair algorithms. Therefore, the inference attack will not work properly. Hence, an attacker will have to use small packets to be able to execute an inference attack. since the times for RTT and peak time are very different for small packets. Then, if someone wants to detect a possible inference attack in an Openflow network, a large number of small packets from different sources to a same destination might indicate that attacks is being performed, but need to be analyzed only during the time interval that the rules are stored in the switches, because the rule will be deleted quickly due to short idle time that is 10 seconds. Hence, it's very unlikely that inference attack could exploit this kind of rule. On the other hand, L2 pairs algorithm is vulnerable to the inference attack because this algorithm does not specify the protocol in the filter, and the source and destination address are defined through wildcards. Although idle time is also 10 seconds, the generic filter will allow many packets match the rule, maintaining it active for a long time. This condition is essential for the inference attack to be effective, hence the L2 pairs should be avoided. In terms of performance, L2 multi and L2 flow visor presented least RTT compared with L2 learning or L3 learning. In this way, L2 multi and L2 flow visor algorithms are the best option to protect the network against inference attack. The results indicate that a wrong packet forwarding choice could affect significantly network measurements. Furthermore, this decision could enable a delay attack to be masked, and Openflow security contributions on trustworthy network measurement could be compromised. To solve this issue, the development of a network measurement monitoring system that establishes a communication with the controller to detect any situation that will influence network time measurement is needed. The results also indicate that an attacker that relies on network time measurement can be mitigated with a right forwarding algorithm's choices, L2 multi or L2 flow visor as an option. Here are the references used in this presentation. And if you have some question, my email is orozco@sapucaia.ifsul.edu.br. Thank you all.